Hello, everyone. Today we start a new chapter, chapter 10. So far, we spent approximately 2/3 of the time of this course, and within this time, we started several essential topics of this course, including all the modeling for claim frequency, claim severity, and the aggregate loss. We also studied risk measures. Those four chapters are likely the essential parts of this course. In the remaining part, we will continue to study something slightly unrelated to what we did in the first two parts. In the textbook, it will be part 4. So basically, we did part 1, part 2, and we are going to skip part 3 because part 3, credibility, is the essential topic for mathematics 5-6-40. We directly move to part 4. It's called the model construction and evaluation. I plan to cover chapter 10 to chapter 12. That is the plan. And if there is extra time, we can take a look at chapter 13, but I doubt we will have time to go there. So that means we begin with chapter 10, okay, in the final part of this course. Chapter 10 basically set down the foundation of what we're going to do in chapter 11 and chapter 12. So let's take a quick look at the overview of this chapter, or the learning objectives. We will basically give introductions to 1 and 2. I mean, those are not new to you. Those are the topics in the first course of statistics. So it's likely that you know parametric and non-parametric, and we have used many times of sample mean, sample standard deviation. Those are point estimators, and you definitely studied before of confidence interval, right? So that's interval estimator. Somehow a slightly more theoretical topic is part 3 here. It's about the unbiasedness, consistency, and efficiency. Those are the properties of estimators. So those are about, well, some measurements of how good the estimator is, once you construct one. And then we will introduce some basics of handling data. They are on the surface level. We don't directly do any programming. We don't handle any actual data. Those will be very simple exemplary data. We study what is left truncation, what is right sampling. Those are quite basic terminologies for data science. So let's first introduce parametric and non-parametric. Parametric is very easy because so far that is what we have been dealing with. For instance, in the claim frequency, let's say we use Poisson distribution to model claim frequency. Here, Poisson distribution is a parametric distribution because everything is known once you know this parameter, right? Similarly, like for instance, we apply Pareto distribution to model claim stability. This is also a parametric distribution. It has 2 parameters, alpha and gamma, right? Depending uniquely at Pareto density. Once you know alpha and beta, there's a unique Pareto distribution. So those obviously are Pareto, are obviously parametric distributions, right? So occasionally, we also deal with non-parametric estimation. A good example would be empirical distribution. Let's say you sample, let's say n IID copies, right? You assume they have the same weight. That's how you calculate sample mean, right? So how do you calculate sample mean? right? What's behind this formula is that you assume for each observation, you assign equal probability 1 over n. There is no parameter, right? It's not parametrized, right? You simply assume all the observations have the equal weight and is 1 over n. So that is right. So you see, each 1 over n is positive, right? And when you add them together, is 1, which means it's actually a probability distribution, right? Although it's a quite trivial one, but nevertheless, this is a distribution, right? We call it the empirical distribution. Um, there's no parameter involved. That's why we call it the non-parametric estimation. The next concept is about point estimator and interval estimator. Again, those are quite naive names. You definitely get all the information from the names only. Let's say you want to estimate the true mean of a population. Then you can sample, right? Then you take the sample mean. Then that is a point estimator, because sample mean is a point, right? So once you do the sampling, it will give you a unique number, right? Of course, if you change a different sample, you'll likely get a different sample mean. But nevertheless, a sample gives you a unique mean, right? You can use this mean to estimate population mean. Okay, so in this sense, you use a number, you use a point to estimate a true parameter. Let's say this is mu, right? Mu is a parameter which you don't know. You are trying to estimate the true population mean. You can do a random sample and then use the mean from this sample as an estimator for mu, right? Then you use a point to estimate mu. Right? But of course, you can also construct a confidence interval, right? Once you get a sample, right? You can use mean plus minus 1 standard deviation or 2 standard deviation, depends on the probability you want, right? So for instance, here when we construct the interval, you can calculate probability, right? We do not talk about probability for point estimator because you are either 100% correct or 100% wrong. And it's most likely you are 100% wrong, because no matter how close your point estimator is to the true one, it's still not accurate, right? Because it's not equal, right? So let's say mu, the true mu is 1. Right? In theory, I don't know, but let's assume I know. Okay, I take a huge sample, 1 million, a sample with 1 million observations. I do a sample mean. Let's say it's 0.99. It's very close to 1, but it's not 1, right? So it means I completely missed the true mean, right? The true mean is 1. What I get is 0.99. It's very close, but not exactly. So that's why we don't talk about probability when we use point estimator. But of course, when you have an interval, you can talk about it, right? So let's say my interval is from 0.95 to 1.05. Well, then that's good, because it includes the true mean 1, right? Then we can talk about probability, how likely this interval includes the true mean, right? So obviously, the wider the interval, the more likely the true mean will be included. But once you have a very wide interval, it has no meaning, right? So let's say I want to know the average age, let's say at UConn. Of course, there would be a true number, right? Because we only have finite people, right, from UConn. So if I really have that kind of time and energy, I can ask everybody. And of course, assuming everybody is participating, giving me the true information, then I can actually get a number, right? And maybe I don't want to ask everybody. Then I take a sample. Let's say I randomly ask someone from campus. Let's say I ask 1,000 students. I use this sample to give me to construct an estimator. I can use sample mean, that is a point estimator. I can also construct a confidence interval. Let's say the average age must be between 0 and 100. Of course, that's going to be a good or not good, maybe an interval that includes the true mean, right? I think everybody agrees. The average student's age at UConn will be between 0 and 100, but such a wide interval has no information, right? What do you get from this interval, right? Is the average age increasing or decreasing, comparing to the national level? No, right? 0 to 100 is just too broad. So there is a trade-off between the chance of including the true parameter and how informative your interval is. Okay, this it's a lot more important because here we discuss some desirable properties we would prefer an estimator to have. The first one is called unbiasedness. The definition is easy. We simply want the expectation of the estimator equals the true parameter. Often confusion, comes from the expectation, because in most cases we have one sample, right? And once you have one sample, theta hat is a constant, right? That's why often people are confused that I only have one constant. Why do you talk about as expectation? That is because you can always choose a different sample, right? Then that will give you a different theta hat. Well, you repeat this, right? You repeat this many times. So it's like a sample of sample. Then you can talk about expectation, right? On the theoretical level, that is because when you do sampling, let's say the true population follows this distribution X. Okay, so it's given by some random variable. Let's say we are interested in the age of students at UConn. Then X denotes the age, right? And then once you sample, okay, what you get is X1, X2, all the way to Xn. So what it means is X1 is the age of the first student included in this sample. X2 is the age of the second student included in this sample, and so on. Of course, when you do the sampling, you don't know the student's age, right? Because so far we haven't done any surveying yet. You only know the values once you ask a particular student, right? So let's put a little bar to denote this is big X, capitalized X. So you randomly select n students, okay? At the selection stage, you can only label them as X1, X2 in capitalized X, because they are random variables at that time, right? Okay. And then, of course, eventually you would ask them to fill out the survey. Once they fill out the survey, it becomes small x. Okay, this is for one sample. Okay, once you have small x's, that's usually what we call observation. Once you have n observations, you have n values. You can sum them up and divide by small n, then you get a sample mean, right? So that is the mean for the first sample. But of course, those observations could be well different for a different sample. That's why we can still talk about expectation, because when we construct, let's say sample mean is constructed as capitalized x1 plus capitalized x2 and all the way to capitalized xn divided by n, not small x. Small x is a specific sample of observations. Okay, that's why here, since all of them are random variables, you can obviously talk about expectation. If the expectation of the estimator equals the parameter you are trying to estimate, then it is called an unbiased estimator. Okay. Sometimes, asking unbiasedness may be a little too strong. So a slightly weaker property is asymptotically unbiased. So here, when the size of the sample, when the size gets bigger and bigger, the mean gets closer and closer to the true parameter. So it's not exactly the equality, but uh, it is still good. Meaning, once you spend more time and energy, you will get a more accurate estimator, right? So that's somehow a good thing. Okay. Uh, Next, what we want to do is um, it's likely that you may be able to construct two unbiased estimators. Well, it's very easy to see, right? For instance, if you want to know the true mean, well, I can just sample one. Right? I can just ask one student, right? And ask his or her age as the sample mean, right? Because well, we always, when we do sampling, we always assume IID, right? So um, no matter what student you pick, we assume his or her age is an IID copy of X, meaning the expectation of X1 equals mu. So in theory, this is an unbiased estimator. But obviously, we all agree that asking one student and using her or his age for the average, for UConn, it's probably not a good choice, right? But it is an unbiased estimator, right? Of course, we would like to use sample mean for some relatively big n, right? So as you can see from here, for any n, right, n can be 1. And if n is 1, this is this case. If n is 2, you ask 2 students and use their average. If n is 3, you ask 3 students and use their average, and so on, right? So they are infinitely, not exactly infinite, but at least from 1 to capital N. Let's say capital N is the total number of students at UConn. But there are many, many choices, right? Which one is the best, right? So which one is the best? Now, of course, you would like to ask everybody then that it is a true value, but there will be some the time and efforts may be too much, right? And in some cases, you might even have infinite many of members in the true population. Then there's no way you ask everybody, right? So anyway, using this simple example, we can see that uh, for the same population, we may be able to come up with more than one unbiased estimator. Then our question is, which one do we choose? So a basic criterion for selection is to choose the one with smaller variance. Right? It's a naive idea. Right? We know they all have the same mean. The one with smaller variance, well, would give you a more accurate uh, estimator, right? Because we can have another one which have more fluctuation. Well, although they have the same mean, but obviously the solid line is closer to the horizontal line, right? It's just obvious. So with that in mind, we introduce this. Given two unbiased, okay, theta hat and theta tilde. Theta hat is better or more efficient if its variance is smaller than the variance of theta tilde. The idea is very trivial, right? Okay. Um, the one of the reasons why we introduce this is because later on we will see that usually there's a trade-off between bias and the variance. Ideally, we would want the bias, to go to 0, variance, also go to 0, but that's only an ideal case. In reality, usually one goes down, the other goes up, right? So there's no way to make them to make both of them to go down or to reduce both of them. So there's a trade-off, right? Maybe sacrificing a little bias could help reduce variance by a large amount. Then this is likely better than using an unbiased one, right? So but anyway, we once we have that, we can define another important property. It's called consistency. Theta hat is a consistent estimator if it converges in probability to the parameter theta. Okay, this is the definition of convergence in probability. It is a slightly theoretical concept, and I don't think we will ever deal with different types of convergency. There are convergence almost surely. There are convergence in probability, as what we define here. There are also convergences in L1 or even LP. For instance, we actually have seen this. Let me go back to. This is usually what we call convergence in L1, right? Because mean is L1. But you can also define LP, right? So there are different types of convergence. We don't want to go into that area. It's definitely beyond the level of this course. That is the reason why we only introduced this definition, but I doubt we will ever use this. What's more helpful is actually theorem 10.1. An estimator is consistent if it is asymptotically unbiased. That is easy to verify because calculating expectation is normally easy, and the variance goes to 0. Okay, this is only if, means this is sufficient but not necessary condition. So later on, whenever you want to verify an estimator is consistent, you apply this sufficient condition. You check whether it's asymptotically unbiased and whether its variance goes to 0. So basically, we want this to go to 0 and the variance to go to 0. Okay, so that's what we want. Those are the sufficient conditions for a consistent estimator. So this is the interesting part. MSE, mean squared error. This is definitely not new, right? When you do the linear regression, this is the thing you are trying to minimize. You are trying to minimize the mean squared error when you do the linear regression. Somehow a useful result is here. Usually we are trying to minimize this, right? Because this is what we are trying to, this is our target. Okay, this is your choice or your estimator. So if you are able to minimize, that means you are getting a good estimator, right? The limit case is when this is 0. If MSE is 0, you get exactly what you are trying to estimate, right? So that's the perfect accuracy, 100% accuracy. But nevertheless, that is probably impossible to achieve. So we turn to an optimization problem. We try to minimize this. So we try to find the best we can, right? So in order to solve this question, we do a little mathematical trick. We insert a constant and we minus, we process same constant, and we easily show this last one is 0. So MSE can be decomposed into 2 terms. One is variance, the other one is the square of bias. So of course, as we can tell from 10.6, bias equals 0 is good thing. That's why unbiased is good, right? Because that means the second term is 0. But when the second term is 0, variance is likely to be high. So their summation may be high as well. So that's probably not good, right? That's why sometimes we are willing to sacrifice a little on bias. So we allow this to increase a little from 0, but we do want to lower variance by a a lot more amount, then we are able to reduce MSE, right? So let's take a look at an example to recap those important properties we just introduced. So we assume we have a sample of random, well, when we talk about random sample, that means those are IID copies of X, okay? Here X follows a uniform distribution from 0 to theta. Obviously theta is bigger than 0. We define Y as the maximum. This is the order statistics, right? So we take Y as the estimator for theta. So we want to calculate everything. We want to know mean, variance, mean squared error. Is Y a consistent estimator? So this is very important. That's because this is actually the max order statistics, because Y is, by the way, this is the notation. When I put a subscript and put wrong bracket to include the number, that means the ith observation once you order from the least to the biggest. So which means here, this means the largest from all. Okay, and similarly, x1, bracket 1 is the minimum. Right? Of course, you can define x bracket 2, x bracket 3, and so on. Right? X bracket 2 would be the second smallest. Right? So it's the smallest, and then you take out the smallest one. Then you take smallest for the remaining n-1 random variables. Right? So so for both smallest and the biggest, you need to know their PDF and the CDF. So let's do this analysis together. So the first one is nothing but definition. This is how we define CDF. Okay. Next, we use the definition of Y. Y is the maximum. So if Y is less than something, all x1, x2, all the way to xn must be less than or equal to Y as well, right? Because Y is the max. If the biggest value is less than small y, then all members of X should be less than or equal to this small y, right? And then we use the independent condition, okay, to write them as independent and identical condition to write that to derive the next equality. And finally, we use uniform. So far to this step, it holds for any general distribution. Okay, we only apply uniform in the last equality, right? Because X is uniform. So X less than Y would be Y over your theta, right? Okay, once you have the CDF, you can simply differentiate, right? By the way, your Y is also between 0 and theta. You can quickly differentiate, and that will give you the CDF, that will give you the PDF of this max order statistics Y, okay? In order to calculate mean and variance, obviously, you can just apply the definition of them, right? By the way, this is actually a beta distribution. So this is a special beta distribution. It's a scaled beta because usually for a standard beta, it's between 0 and 1. For instance, let me give you this definition. Then I can write the PDF as x alpha minus 1, 1 minus x, beta minus 1. So this is a beta function. So basically just the integral of your numerator. So here your x is between 0 and 1. So this is beta distribution. So when you do a quick comparison, you can see that here your y is between 0 and theta. It's not 0, 1. Well, obviously you just need to do a proper scaling, right? So y divided by theta then will be between 0 and 1, right? So y divided by theta then is a beta distribution. As you can see, alpha is equal to n, beta is equal to 1. So it's a special beta distribution. Once you can identify the beta distribution, you can use the known results of beta to get mean and variance. But here, since it's a very special case, right? So we can actually do the integral directly, and it's a very easy one because it's a power function. So it's somehow easy to show this. As you can see from here, obviously this number does not equal to theta. Again, theta is something we're trying to estimate. So it is not unbiased, right? It means it's not unbiased. So it's biased. And we can actually calculate the bias. But the good thing is when n goes to infinity, right? So this obviously approaches theta. That's very obvious to observe. So it's actually asymptotically unbiased. So from here, it's obvious that your y is a function of n, although we don't write it explicitly. That's why we take a limit when n goes to infinity. The expectation of y will change because it actually depends on n. But in convention we don't write it. Then we calculate the second moment. Once we know the second moment, we know variance, right? Here the bias is actually negative, so you always underestimate for the true parameter theta. So it's a downward bias or negative bias. From the variance part, we can see it's given by this. It's very obvious that when I take n to infinity, the variance of the estimator y will go to 0. So that's good, right? So we have asymptotically unbiased plus variance goes to 0. So we can claim this is a consistent estimator, right? So by theorem 10.1, this is a consistent estimator, okay? By the way, you can try to reason the what is the definition? Here's the definition. You can try to reason that you can try to calculate because you do know the probability, right? For any delta, right? You can just pick the positive delta and try to compute the distribution, because here what we want is, right, not given any delta, right? So here you are trying to calculate y or not here is delta, right? So what is the distribution? Distribution is here, right? So first of all, the right-hand side, we don't need to care, right? Because it's always truncated at theta, right? Y is always between 0 and theta. So the right-hand side is automatically satisfied. You don't need to care about it. So we just need to do 1 minus. Okay. This is less than 1, right? Of course, it's also let's pick a special theta delta. Let's say delta is between 0 and theta. Then it's always between 0 and 1. Right? So from here we see that when n goes to infinity, this guy goes to 0, right? So the entire probability goes to 1. So that's exactly the convergence in probability. But in most case, well, you don't need to do that. Okay, so that is the property. So how about this? I give you a slightly different modification. In this example, your x is a uniform from 0 to theta. You try to estimate the up limit theta, right? And what you do is you construct the max order statistics and use it to estimate, right? And once you get this, well, you can always try a different one, right? I can get, this is also an estimator for theta, and right. So you can always get an unbiased estimator if you want, right? But of course, this will, because this is greater than 1. So when I get an unbiased estimator, the variance obviously blows up, right? And if you do a little simplification on this result, you will see this will be 1 plus 2 divided by n plus 1 over n squared. Okay, the good thing is, as n goes to infinity, well, the extra part is minimum, right? It goes to 0, right? But nevertheless, your variance goes up. So there is a trade-off, right? By using x hat, I will get an unbiased estimator, but my variance goes up. So the MSE will we will need to calculate to see whether MSE goes up or not. But anyway, you can carry out the computation for MSE of y, right? That's very easy. So what I want to ask you is, so let's say here's an example. I consider something slightly more general. Okay, so here both A and B are unknown. So what you can do is you try this. You repeat the same thing, because right now what we are trying to estimate is the lower parameter A. So you repeat the same analysis, and I ask you to calculate the mean, the variance, the MSE of x bracket 1. So it's the minimum, right? The min is the minimum order statistics. And is this one a consistent estimator to A? Right. So well, here you can assume B is given. B is known. Okay. But A is something I don't know. Okay. You use the smallest order statistics to estimate it and try to study the properties. Okay. We will end here for this video. In the next one, we introduce basic terminology of data.